It's bound to happen at some point. Okay. All right, so last time we were talking about combining functions using addition, subtraction, multiplication, and division. While I have this out, I was, before I get back into this, I had written out like a rubric, well, mostly a key to the graphing homework that like half of you submitted on D2L. I guess I just wanted to give you guys an idea, and I am going to post this on D2L, so you will be able to see it. But when I'm doing the graphing, I mean, I have graph paper. I have obscene amounts of graph paper. If you don't have graph paper, it's not a big deal. For some of these functions, they're pretty basic. So if you're familiar with functions like f of x equals x and f of x equals negative x, and you're doing these piecewise functions, you don't have to show me a table of values. But if you would like to include a table of values to show your work, that is a really good idea. Some of you will need that, and that's fine. I'm going to be telling you on your exam for any of the graphing, since I can't actually be giving you an actual like copy of the exam with a coordinate grid on it, you're going to have to be making your own if I ask you to do your own graph. So if I ask you to graph a piecewise function on your exam, I'm going to say label your axes and mark the scale so that I know what your scale is. I don't need you to do anything super crazy for the scale. When I say label your axes, that just means label them as far as x and y. Super straightforward. That's all you need to do there. And as far as the scale is concerned, just give me some sort of indication on both the x and the y axis about how many units each one of your squares will represent, just so I have some sort of idea. You don't have to label every single tick mark that you create, as long as you label at least one of them, just so I can see how many ticks each value is counting for. That's completely fine. Just make sure you do that on both the x and the y axes. Most of the time, your scale is probably going to be 1-to-1. But I don't know, sometimes we have really large things to graph. And then, you know, if you have to go up to like 27, then you might want each box to represent 3 units instead of 1. And I find that students do that a lot. So that's kind of up to you. But this is kind of what I would be expecting to see for piecewise functions. If it was something that was a little bit more involved with, you know, more extensive quadratic function, then I would expect to see more work. But for something like y equals 1/2 x, I mean, it's just the slope of 1/2, you know, the rise over run is just rise 1, run 2. But if you want to plot points, that's totally fine also. And then for something like this one on the bottom, I have this dotted line showing the line, but just because I used a y-intercept of 2, it's dotted because it technically doesn't appear on the graph. I have a circle here that's open because for the function x plus 2, that only occurs if x is less than -3, not equal to -3. Note that it's still a function because you can draw a vertical line through it at -3 and you're only going to hit the graph one time. So that's what I wanted to say about the piecewise graphing. If you did not do the graphing from 2.2 and 2.5, I would still look at the key anyway, and I would still do it as good practice for your test on Monday. Your test is Monday. My goal is to have it available to you at 6 p.m. I'm probably just going to release it on D2L. This is something new that I don't usually do. We're in uncharted territory here. But my goal is just to make an announcement on the front page of D2L that's available to you at 6 p.m. saying, here's your test. And then any special instructions I had for it, if there are any, would be included in that. So at that point, you could open it in D2L, you could download it. If you have a printer and you wanted to write directly on the test like you would in class, then do that. Otherwise, you can just take the exam and then just take some blank paper and, you know, start writing it out. Like number 1, blah, 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 put your work there. Number 2, put your work there. You know, label it, space it out. If you feel like you're the kind of person who likes to skip around and maybe do the second page first, that's fine. But just please try to keep it in order and keep it nicely labeled so that I can see what's happening with your work. You are going to get the entire class period to do the test. So you'll have from 6 to 7:50 to finish it. Most of you will not need that time. Some of you will take the whole time. That's just from my experience with teaching college algebra. Any other questions about the test? Okay. Wonderful. I will most likely shoot you an email over the weekend. Oh, I did, by the way, put up a review assignment on my math lab. I think for some reason I set it to be available at 7:40 today. I don't know why I did that, because I made it several hours ago. But it's actually a review test. So it doesn't work the same way that my math lab homework works. If you decide you don't like it and you prefer a review homework, I can do that next time instead. Just let me know. The review test, I think, will maybe make you feel a little bit more like you're in a testing environment because you won't get that immediate feedback like you would on homework. So you're just going to submit your answers and you'll, just say, okay, and it's not going to tell you whether it's right or wrong because it's a test. So if you want me to turn it into a homework, I can. It's really a pretty easy thing to do. Just take those same exercises and shift them over. I think it's 33 questions. That's probably longer than what your test is going to be, but it's in that neighborhood. Your test will probably be closer to 25 questions. My math lab test, though, will take a little bit less time since some of the graphing on my math lab is multiple choice. And on your test, you're going to have to graph by hand, stuff like that. So it might even be 20 questions. I don't know. I have not finished writing it yet. So we shall see. Anything else? Questions about the exam? By the way, the review assignment is optional on my math lab. You don't have to do it. I just put it up there because it's, just kind of a synopsis of what we've done in case you want to, it's been a while since you've done some of that stuff from 1.1 and 1.5. Just thought it'd be a nice reminder. If you choose to do it, you don't have to do it. Okay. Let's continue talking about these topics in 2.6. Last time we left off with combining functions and finding their domains. We're still going to be working with finding domains today. The difference is that we are going to be working with composite functions. And we're also going to be using composite functions with 2.7, which is the last thing we're going to do today. It's pretty quick. I don't expect this will be super long, so hopefully we'll get done a little fast. I don't know. We'll see. The composition of the function f with g is denoted f. This is a circle. It ran into the g. It looks like fog. It's not a dot like a multiplication symbol. It's just a little circle that would be in the middle between those two letters, and is defined by the equation f of g of x equals f of g of x. So this is read f of g of x. F of g of x. Sometimes people call it fog. You can call it fog if you want. Sometimes it's going to be goff because you're going to take g of f of x. So that's a way that we would say this composition. Now, in a few minutes, we're going to start talking about the domain of the composition. First, we're going to focus on finding the composition. So let's skip over this domain piece for now and just talk about how to find the composition of two functions. You've actually done this before in this class. We did quite a bit of it in section 2.2. So it should not be completely new to you, but the notation might be very new to you today, although I'm guessing you've seen it at some point in your lives. For the given functions f and g, find the indicated composition. So we are going to be finding f of g of 8. And I did not note here to find f of g. So let's first, that's fine. I just asked you to find f of g of 8. We'll do another composition on the next page. When you see f of g of 8, and again, this circle ran in here, really it looks like this, f of g of 8. What I generally ask students to do is just rewrite this from the get-go. Even though this is the official notation for the composition, it makes more sense to us to read it as f of g of 8. Now, there are two ways of finding this composition. One thing you could do that takes probably a little bit longer is to find f of g of x and then evaluate that at 8. But since in this case you're only being asked to find the composition evaluated at a number, we can go ahead and just find the inside function first and then evaluate f there. So you are being asked to find f of g of 8. So let's think about g of 8 as being its own separate value, and then we're going to evaluate f at that value. So we're going to say first find g of 8. To find g of 8, we're just going to look at our function g of x, and everywhere we see x, we're going to swap it out with 8. So I'm going to rewrite the g of x here. It's 8x minus 5. And we will find g of 8. Everywhere we see x, we're going to swap it out with 8. And then we'll evaluate. Make sure you're using the correct order of operations. 8 times 8 is 64, minus 5 is 59. Don't put a box around it yet because you weren't just asked to find g of 8, you were asked to find f of g of 8. So we now know that g of 8 is 59. So we're going to use this information. I know I just said don't put a box around it, but I want to make sure that we're calling it out for what it is. It's g of 8. And then the next thing we're going to find is f of g of 8. So when I'm looking for f of g of 8, I know that g of 8 is 59. So I'm actually looking for f of 59. So we're finding this new value at which we have evaluated this function g, and we're going to evaluate f at that value. So now that I know I'm looking for f of 59, I can go ahead and use our function f and then evaluate it at 59. So I know that f of x, I'm going to rewrite it here, is 17x squared minus 6x. And then we'll use that function to find f of 59. So everywhere I see x in both terms, I'm going to sub it out with 59. So I have 17 times 59 squared minus 6 times 59. Now, if you enter this properly in your graphing calculator, in your TI, it should do all the order of operations for you. If you do this piece by piece, just make sure you're correctly applying the order of operations. Oh, it's not actually equals 7. It's an arrow. You guys are so good. That makes sense, Angel? Sorry, I'll make my arrows less like equals 7s. All right, let's see if my lighting situation is right today. It's probably not. I should just give up on this. We're all still waiting for emulators. 17 times 59 squared minus 6 times 59. And then you get a very large number, 58,823. And that is the value for f of g of 8. Does anyone have a question about how we found that value? Okay, so sometimes you're going to be asked to evaluate the composition at a number, and sometimes you're going to be asked to evaluate the composition at another function, which is what we're going to do next.
So would both of them be our answer?
This is your actual answer. This is just part of it that got you to where you needed to go. So sometimes I put boxes around things, not because I'm done, but because I don't want to lose it. Because sometimes you have a lot of information, so it's easier just to kind of box it off so you know that it's like an important piece. But the 58,823 is our final answer. Yeah, sorry, I don't know who said that, but were there other questions? I thought there was maybe someone else who was asking a question. Okay. Wonderful. So let's continue talking about evaluating these compositions. The next one we have is we are looking for f of g of x. Sometimes my fonts are fine and then I open them as PDFs and they get all funky. F of x is 6 divided by x minus 3. G of x is 4 divided by 7x. So we're going to find f of g of x. Remember what I was saying with the first problem. When you're given your notation for the composition, and again, because it looks kind of funky, I'm going to rewrite it. So this is what we're being asked to find, f of g of x. Rewrite that to be f of g of x. Okay. Now we're going to take our function f, and everywhere we see x, this time we're going to replace it with g of x. Now, we have done this before. We did it especially, if you think back to 2-2 when we were doing those special quotients. What were they called? I don't remember. I never remember what those things are called. Quotient 2-2. But I'll find it. The difference quotient, yeah. We evaluated f of x plus h minus f of x divided by h. We're doing the same thing here, just slightly different notation. So we're going to take our function f, that's our outside function, and instead of using f of x, we're looking for f of g of x. That means everywhere you see x, we're going to replace it with g of x. So going back to our function f, everything stays the same except for your x. So we have 6 divided by x minus 3. Well, when we now sub it out with g of x, we're going to have our function g of x in place of x. So we're going to sub it out. Some students find this kind of odd at first, but I think you get the hang of it pretty quickly. So in place of x, we have 4 divided by 7x minus 3. Sorry, my parents are babysitting, and clearly they don't understand that I hear everything going on out there. Guys, can you be quiet, please? Go downstairs. Sorry about that. Okay. Are there questions here? Because I feel like this is the hurdle. It's very subtle. It happens very quickly. But as long as you get to this point, that's where a lot of your points come from. And from there, I feel like it's a little bit more intuitive what you need to do to simplify.
Do you have to put parentheses around G?
You do not have to put parentheses around G in this case. In a lot of cases, you do need parentheses around G if G is more than one term. So if G was something like x plus 2, Well, in this case, I guess you would just be subtracting, so you wouldn't need that. It kind of depends on the situation. When in doubt, feel free to always use parentheses anytime you drop in an expression. But in this case, because we just have one term, swapping it out for another term, you don't need them. Great question. Other questions here? Okay, wonderful. Now, officially, yes, you have an expression that is f of g of x. Yay! If you enter this in MyMathLab, it's going to tell you no. It's going to say your answer is equivalent to the correct answer, but it is not written in the proper form. The reason why is because this expression is not simplified. This is called a complex fraction. Complex fractions are not simplified. Now, if you took Math 98 at ACC, you had a whole section where you learned to take expressions like this and simplify them. You were given two methods to do so. I tend to always use the same method over and over again. By the way, you see stuff like this in calc all the time, and you're going to have to simplify it when you get there too. So if you're thinking, ugh, like, why am I doing this again? I'm never going to use it again. This is something that you're going to have to do all the time. And you're going to be doing it more in this class. So let's go ahead and simplify this complex fraction. One of the methods for simplifying complex fractions is to multiply every term by the LCD. To simplify, I keep running my hand into my document cam. Multiply each term by the LCD. Now, that is one method for simplifying complex fractions. You do not have to use this particular method. You can also simplify the fraction in the denominator and then simplify the fraction in the numerator. It's kind of up to you. But this is the method that I tend to use because personally, I feel like it's the easiest way to do this. So let's go ahead. I'm going to rewrite the expression just so that we have it isolated down here. Now, when we say multiply each term by the LCD, you need to find the LCD of all of the fractions first. In our case, we only have one quantity that's in the denominator officially. I know you're technically looking at two denominators. Yes, this whole entire expression is in the denominator, but when you're multiplying by the LCD, you're only looking at these subdenominators. And if you only see one value in the subdenominator, that's your LCD. You're going to need an LCD regardless of what method you choose. Some students like to combine the fractions in the denominator by multiplying this guy by 7x over 7x, and then they invert and multiply. That's the other method. I'm going to multiply each term by the LCD, which is 7x. The whole point of doing this is what you're trying to do is get that subdenominator to cancel out so that you don't have a complex fraction anymore. So if you do not choose the correct LCD, then you're not actually going to be simplifying your complex fraction. And by the way, if you wanted to practice this particular skill, I can, in the office hour, let you know of a section in Chapter P that has problems like this for these rational expressions. That'll give you some extra practice. Let's go ahead and simplify. When you multiply by 7x in all three terms, you're going to get this denominator to cancel, which is exactly what you want. The rest of the expression stays. 6 times 7 is 42. We still have an x that we're carrying over. In the denominator, you still have a 4 minus 21x. This is the simplified version of your composite function. Now, on a test, I don't have a box that pops up and says, although your answer is equivalent to the correct answer, it's not correct. So technically on an exam, if you left your answer like this, I would give you partial credit, but you wouldn't get all the credit. And you'll find that if you keep going for, well, maybe I can get partial credit on this, you lose points here, you lose points here and there, they all start to add up. So really try to simplify all the way so you're not getting this situation where you would have had an A-, but now you have a C+ because there were all these little things that added up. Now, does anybody have a question on number 12? Okay, so anytime you have a complex fraction in your answer that has to get simplified, you must get rid of it. Number 13, we're going to perform this composition, which again, the font got all screwy. We're being asked to find g of f of x. So you're not always going to see it in the same order, and sometimes you'll see functions with different names. They're not always going to be f and g. Does someone have a question? No, oh, I thought I heard someone go off mute, but it turns out my speakers are just making bizarre noises. It's not good. Okay. When you're finding g of f of x, just write it out as g of f of x. Now you're going to take your function g, and everywhere you see x, you're going to replace it with f of x. So our function g of x is 4x plus 10. We're going to take that and evaluate g of f of x. Everywhere we see x, we're going to swap it out with our whole entire function f of x. So that means that this x right here is going to get replaced with f of x. So let's go ahead and keep anything else that is not x in here. So the 4 stays, but the x now becomes f of x, which is a fraction. So you have 4 times your variable, which is now x minus 10 over 4, and then plus 10. And then simplify. And again, just filling out this composition is where a lot of your points are going to come from. Simplifying it is important. I would aim to do both, but make sure you're at least doing something. Does anyone have a question about g of f of x before we simplify? Okay. All right, these functions are actually related to each other in a special way that we're going to look at in 2.7. But go ahead and simplify. Notice that you have 4 times a quantity where 4 is in the denominator. So you can actually go through and cancel these 4s in that first term. And when you cancel the 4s, that leaves you with x minus 10 plus 10. X minus 10 plus 10 is just x. So g of f of x is x. Every once in a while, you're going to be asked to find, for instance, g of f of x, and then the second part of the question will say find g of f of 4 or something like that. If that's the case, use this expression for g of f of x to evaluate it at some sort of number if you're being asked to do so, which you will be asked on your homework to do both. So once you find this value, it's going to be much easier to evaluate any other expressions from there. So this is your g of f of x. Okay. Now we're going to bring in the domain. The following values must be excluded from the input x. If x is not in the domain of g, it must not be in the domain of f of g. Any x for which g of x is not in the domain of f must not be in the domain of f of g. I'll just do that. So we're looking for two things. If some value x is not in the domain of your inside function g, then we're going to exclude that from the domain of the composite function. And any x for which g of x is not in the domain of f, that means look at your final answer for your composite function. Exclude any values that make the denominator 0 or any values for which the radicand will be less than 0. So I'm going to give you a couple of examples for finding the domains of composite functions. By the way, keep in mind, this assumes that your function, your composite function is f of g. If it was reversed, if it was g of f, then you'd be talking about x not being in the domain of f. It's always whatever that second function or inside function is. Find the domain of the composite function f of g. In order to do that, first we're going to look at g. Any x that's not in the domain of g is going to have to be excluded from the composite function. However, g is a polynomial function. You don't have any variables in the denominator, and you don't have any variables under radicals. So the domain of g is all real numbers. Because the domain of g is all real numbers, the only thing we really need to focus on is just the domain of f of g of x. So you check your inside function first, and then you go ahead and find the composite function. So let's go ahead and find f of g of x. So we're going to use our function f. Everywhere we see x, we're going to swap it out with g of x. So for our function f, the 2 stays right where it is, but instead of having x plus 9, you're going to write in g of x plus 9. So x plus 5 plus 9. So the 2 stays, the 9 stays. The only change is that instead of having x, we have g of x, which is x plus 5. Does anyone have a question here? Okay. All right, now we just need to simplify. So I have f of g of x equals 2 divided by x plus 14. We already checked the first condition. We found that the domain of g was all real numbers, so we didn't have any issues. The second thing to check is the domain of your composite function. Now, your composite function will have a denominator of 0 if x is equal to negative 14. Note, and we talked about this earlier in the section, remember you're looking for values for which the denominator would be 0, and that will occur when x equals negative 14. But a lot of you guys will eyeball this for these linear expressions in the denominator. So go ahead and write out the domain for f of g of x such that we're going to use any real number excluding negative 14. So the domain of f of g of x is going to start at negative infinity. You're going to work your way up to negative 14. But you're not going to include negative 14. You're going to pick your interval back up again and send it off to infinity. So this will be any real number except for negative 14. So we found the composite function. That was one of the things we had to do. And then we found the domain of the composite function. Well, I guess technically I didn't explicitly say find the composite function, but you kind of have to find it. Are there any questions on number 14? Okay. Wonderful. All right, let's find the domain of the composite function f of g of x, where f of x is the square root of x and g of x is 5x plus 20. First of all, we're looking again at f of g of x. Focus on your inside function first. The domain of g of x is all real numbers, so we don't have to worry about excluding any values based on g. G is a polynomial. So let's go ahead and find f of g of x. Oh, this was an instruction from the previous page, but I want to make sure we are all clear on what's happening. So I'm rewriting the instruction. So to find f of g of x, we're going to take our function f, and everywhere we see x, we're going to swap it out with that expression g of x. So we're going to have the square root of not just x, but g of x. G of x is 5x plus 20. This is the composite function. To find its domain, we already looked at the inside function. Let's just focus on the composite function itself now. We need to verify, or we need to enforce, that the expression under the radical is always going to be greater than or equal to 0. We can't have it be negative. So let's go ahead and set up an inequality using the radicand, making sure that it's greater than or equal to 0. And then go ahead and solve your inequality. You have 5x is greater than or equal to negative 20. Now, last time I reminded you guys about solving linear inequalities, and we said that anytime you multiply or divide on both sides by a negative number, you need to switch the direction of the sign. That does not apply here. Notice that when you are dividing in this inequality, you're not dividing by negative 5. You're taking negative 20 and you're dividing it by positive 5. So make sure that you know when to flip the sign and when not to flip the sign. In this case, you're dividing both sides of the inequality by a positive number. Just because the right-hand side is negative doesn't matter. You're not dividing by a negative. So we don't flip the inequality symbol in this case. We just need to ensure that x is greater than or equal to negative 4. In order to write that in interval notation, we're going to start at negative 4, and we're going to put a square bracket on it because we can include negative 4 in the interval, can be equal to negative 4. And then we're going to include any value that's greater than negative 4. And this is the domain of f of g. Any questions on 15? Okay. Awesome. I want you guys to try 16 and 17 while I finish attendance. I feel like these are either going to be extremely clear to you or they're going to be extremely confusing. So if you don't get it right away, that's fine. I'm going to go over them in a minute. But what you're going to do is you're going to write functions f and g such that h of x is the composition f of g of x for both of these. So think about it, see what you come up with, and I'll go over it in a minute after I finish my attendance. Does anyone want to volunteer what they set as functions f and g for number 16? Oh, Gian, oh, I forgot. You've got that whole issue with your microphone. If you think you can type it out, you be my guest, Gian. Oh, she's typing. All right. F of x equals 1 over x plus 2, and g of x is x squared plus 4. Interesting. Let's write this down. That is not what I would have gone for, but let's see if it works. You typed it out beautifully, by the way, with all your parentheses. Okay, so if we do a composition here for f of g of x, then everywhere we see x, we're going to swap it out with g of x. So we have x squared plus 4 plus 2 is 1 over x squared plus 6. Gee, and we have a minus 6. Oh, shoot. You know what, though? Actually, if this had been a plus 6, that would have been great. I never even would have thought about something so complicated. It doesn't have to be this complicated. Yes, it was a minus. No worries, Gian. That was actually really interesting. I'm glad you said that. Did anyone else have something that was much more straightforward, but maybe slightly less interesting? But that doesn't take away its value. We don't have like a raise hand thing, do we? You know, I keep thinking maybe I should switch to Zoom. I only do you guys like Zoom better? I just have more experience with it now that my kindergartner is using it every day. Okay, Angel says f of x equals 1 over x, g of x equals x squared minus 6. Yeah, that was what I would have done. Now, you absolutely don't have to do that. You could have done what Gian did and kind of just changed the numbers a little bit, and it still would have worked out. If we had had a plus sign, yes, this would have been perfect. I'm going to erase this, though, because I don't have any more space. I hate erasing things because I like to have some sort of documentation that we did this, but I don't have the space right now. Okay, f of x is 1 over x, and g of x is x squared minus 6. Let's see. Oh, now I'm looking at, oh, Beth had a good one too. Yeah, we can show that too. This one is probably the most straightforward. Beth's will also work. F of x is 1 over x, and g of x is x squared minus 6. A lot of these are set up so that there's nothing too crazy going on. You don't have like 2 terms or anything in the fraction. So you can just set up your outside function to be a generic reciprocal function. And then your inside function is the one that gets a little bit more specific. So this would be a good one. Sorry, I chopped off my 6 here. And then I'll write down the one that Beth included. So we'll say also, let's see, f of x equals 1 over x minus 6, and g of x equals x squared. And in that case, yes, if you evaluated f of g of x, you would indeed get x squared minus 6. So yeah, that's a good one too. Good. So I actually like that we had some different ones here because I want you to see that there are a lot of different ways of setting up these compositions. We'll do number 17 also, but did anyone have a question on 16? Okay. So either one of these are good options. Either one of these is a good option. For 17, did anyone want to volunteer? Angel, would 17 be, yeah, you know, Angel, that is exactly what I would do. Would 17 be something like f of x equals the absolute value of x and g of x equals 6x plus 8? Yes, absolutely. I think that would be probably the most straightforward. Your outside function is just the basic what is happening in this problem, which is, in our case, the absolute value. And the inside function is that more specific piece. So the f of x would be the absolute value of x, g of x would be 6x plus 8. Good. Did anyone have anything different for 17 that you wanted to share? I don't know what else you would do with this one, but students always surprise me. I never know. Okay. So there'll be some of those on your homework. It won't be as interesting on my math lab, but I'll probably put one on your test just to sort of make sure that we can work our compositions in both ways. Okay, that was 2.6. So a lot of things happen in 2.6. 2.7 is much shorter. We're just going to be talking about inverse functions. Some students really love 2.7. I always really enjoyed 2.7. And for some reason, the process for finding an inverse function is very intuitive for students. They don't forget it. I don't know why. There's something about it that just, I don't know. Good stuff. What we're going to be doing here first is verifying inverse functions. Now, I'm going to be asking you to do two things here as far as finding inverse functions. One of those things is finding inverse functions. Another one is verifying inverse functions. Verify is not the same as find an inverse function. There's a process for verifying whether or not your functions are inverses of each other. Now, we are going to talk in a few minutes about what it means to be an inverse function. First, we're going to talk about how to check to see if your functions are inverses. And then you will find that you actually know a lot about inverse functions. You just never knew that's what they were called before. Let f and g be two functions such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f. The function g is the inverse of f and is denoted f inverse, which is like an f with, it looks like a little exponent of -1, but it's not actually an exponent, it's just the notation. So it looks like f to the -1st power. Thus, f of f inverse of x equals x, and f inverse of f of x equals x. And the domain of f is equal to the range of f inverse and vice versa. It's actually pretty cool once we start working with these inverses and you kind of see how they operate. That means when you're being asked to verify inverse functions, what you're going to check is the composition. When you're verifying, you're checking the composition. Oh, let's see. Check that f of g of x equals x, which is also equal to g of f of x. Because in a few minutes, I'm going to show you how to find inverses, and students always will do that instead of verify. When I say verify, I want you to do the composition. If you don't do the composition, you're not going to get the points for it. Verify means compose. Verify that you end up getting x as the composition for both f of g and g of f. Okay, so number one, determine which two functions are inverses of each other. We're going to do this by checking the composition and seeing which compositions give us x in both directions. So I need to find two functions such that, for instance, f of g equals g of f, and they're both equal to x. So first we're going to check f of x and h of x. I mean, technically, I guess we could pick either one because this is multiple choice, but we might as well work with the options that we have. If I'm trying to find whether or not f and h are inverses of each other, I'm going to use some composition. I'm going to find f of h of x. Now, the nice thing here is that if I don't get x when I work on this composition, that means they're not inverses, and I don't have to go through the work of taking h of f. If it doesn't work one way, just forget it. You're done. Try a different set of functions. So let's find f of h of x. So for f of h of x, we have the square root, and then h of x is x squared. So instead of writing x, we'll write in x squared. Now the square root of x squared is indeed equal to x. Remember that a square root is really a 1/2 power. 2 to the 1/2 is 1. Or you can think about this as being the square root of a quantity squared is just whatever that radicand is. But we used this when we talked about the square root property in 1/5. Okay, now you have an x that's very promising. Check it the other direction. Check to see if h of f of x is equal to x. And if it is, then we'll know that these two are inverses. So h is x squared. Everywhere you see x, you're going to replace it with f of x. So the h function squares the quantity, and then the inside function is going to be this function f of x. I know, for some reason it looks funnier when you do it that way. So h takes the quantity and squares it. F in this case would be your inside function. And the square root of x squared is x. So determine which two functions are inverses of each other. Yay, A was the correct answer. They're both inverses. But I want to show you why the other functions are not inverses of each other. So we're going to say f of h of x equals h of f of x, and both of them were equal to x. That's how you know they're inverse functions. So let's say we had instead started with b, and we would have tested f and g. Well, we could have looked and we would have said f of g of x is, and now f is going to take the square root of the function. G of x is a quotient with x under the radical in the denominator. This definitely does not equal x. So in this case, we can say don't even bother. Checking g of f of x. These functions are not inverses. Of each other. And that will happen too. You'll check two functions, you check one composition, and it's definitely not equal to x. It doesn't matter what it is. If it's not equal to x, they're not inverses. So that means f and g can't be inverses. We already looked at f and h. If you wanted to look at g and h, you could try that in either direction. Let's just do it in alphabetical order. We could have checked g of h of x. Well, g has a 1 in the numerator and a radical in the denominator. And it takes the denominator and takes the square root. H of x is x squared. If anything, this is good practice for composing functions. Now the square root of x squared is x, but you end up with 1 over x, which is not equal to x. So you can stop. They're not inverses. That is how you verify. So when I ask you to verify, don't go through the process and prove to me that one is the inverse of the other just by finding the inverse function. You must show me the composition when you verify. Any questions on verifying inverse functions? All right, now we're going to talk about finding inverse functions. When I ask you to find an inverse function, generally I just give you one function and I say, find this function's inverse. When I ask you to verify, I give you two functions, and that's when you're supposed to perform the composition. In this case, you're given one function in each one of these examples. Now there's a process for this. The equation for the inverse of a function f can be found as follows. Step 1. Replace f of x with y in the equation for f of x. So you're going to change f of x to y. And let's go ahead and work on this in number 2 while we go through these steps, and you can kind of see how they work. So replace f of x with y, no problem. Everything else stays the same. The next step is to interchange x and y. That means switch them out. Everything else stays the same, but y changes to x and x changes to y. So instead of y equals 7 over 6x minus 5, it's x equals 7 over 6y minus 5. That is step 2. Now, step 3 is to solve for y. We'll read the rest of step 3 once we've done that. Sometimes the hard part here is just in solving for y. If you're not sure, if your y is in the denominator, there's no way that you can solve for y while it's in the denominator. So you're going to have to move it somehow. So go ahead and multiply both sides of the equation by 6y minus 5, or think about it as cross multiplying if you like that better. When you do that, make sure that you include parentheses on the left-hand side. So I'm going to show the whole thing just so you can kind of see where it came from. So I took this equation here and I multiplied by 6y minus 5 on both sides. As long as we multiply by the same quantity on both sides, we have kept the equivalency. And now I can get rid of that y in the denominator. The whole thing goes. Before I continue, does anybody have a question so far? Another key here is that we can't solve for y while it's inside parentheses. So we're going to have to distribute. So 6xy minus 5x equals 7. Now, there are a couple of different things you could do at this point, but if you know you're trying to isolate the term that has y in it, get rid of any term that doesn't have y in it. So for instance, this 5x, move it to the right. So now you'll have 6xy equals 7 plus 5x. Now to get y by itself, to solve for y, divide both sides by 6x. And that leaves you with y equals 7 plus 5x divided by 6x. I want to make sure this is clear where this all came from. I'm going to go back and read the rest of step 3. Does anybody have a question about how we solved for y? Sometimes students get really stuck on that. So if you do have a question on it, please ask, because it is something that comes up quite a bit. Okay. So the second part of step 3, if this equation does not define y as a function of x, the function f does not have an inverse function and this procedure ends. If this equation does define y as a function of x, the function f has an inverse function. So basically what you're being asked is this a function? If you're not sure, you can always graph it in your graphing calculator and verify that it passes the vertical line test. But there's nothing that would keep this from being a function. If you remember back in 2.1, we talked about determining whether or not equations represented functions. And when we did that, all we checked was we just wanted to make sure that if we put in a value for x, we could never get 2 different values for y. So any value that we would plug in for x here could only ever give us 1 value for y. And that's the key. So this expression on the right does indeed represent a function. Because of that, then we're going to do step 4, which is swap out y with f inverse of x notation. And then you are done. Now, I'm not going to force you to verify these. If you're not sure about the work that you've done, you are more than welcome to verify these on your own. It's not too crazy. In order to verify them, you would just take f and compose it with f of x and show that you do indeed get x both times. Does anyone want to see that? Would you find that helpful? I only see like 3 people right now. And they don't seem excited about verifying. Okay, that's fine. You can always compose f and f inverse and verify that you get x if you are not sure and you want to check that. I wanted to show you a couple different types of functions that you were going to see here. 2 was one of those functions. Number 3 is a cubic function. We can go ahead and find the inverse for f as a cubic function also using the same process. So we're going to replace f of x with y. And then we are going to interchange x and y. So swap them out. And you will get x equals y plus 6 cubed. So we've done steps 1 and 2. Step 3 is to solve for y. Well, you can't solve for y while it's inside a quantity that's being cubed. You must remove it from the parentheses before you can isolate it. So in order to undo the cubing that has occurred here, similar to the square root property, you instead of taking the square root on both sides, you can take the cube root on both sides. You can take the cube root of y plus 6 cubed, and you don't have to do this in 2 steps. I'm just filling it out in 2 steps in my notes so that it's very clear. And this is the cubed root of x equals, and these two, the exponent and the index will sort of cancel each other out, and you're left with y plus 6. Now, someone's probably thinking, why didn't she use a plus or minus sign? Normally, when we use the square root property, we take the square root of both sides, and then we must apply a plus or minus sign. And I've been hammering it into you because it's so important and it gets forgotten so often. However, anytime we take a cube root or a 5th root or a 7th root, any odd root, we don't need to account for a plus or minus sign. And that's because of the fact that we can take a cube root of a negative and we don't need to worry about losing that negative sign when we square something or taking it to an even power, since we can get that value without having to worry about losing it. So when you take a cube root or a 5th root or any odd root, you don't need to worry about using a plus or minus sign. It's only with even roots. Does anybody have a question there? Okay, so you're almost done. You're going to subtract 6 from both sides, and you'll get the cube root of x minus 6 equals y. And then you're going to determine whether or not you have an inverse function. You definitely have an inverse equation, but is it a function? Well, look at what happens anytime you substitute a value for x into this expression on the left. Any value that you substitute in for x is going to get a cube root, and 6 is going to be subtracted from it. There's never going to be an instance where you're going to get 2 different solutions to pop out for y. Because of that, we can say that y is f inverse of x, and f inverse is the cube root of x minus 6. I flipped the direction there because I prefer to have the y on the left-hand side. And again, you can verify that you have an inverse function by composing the two. Questions here? Okay. Number 4, f of x equals the square root of x minus 7. You guys do this on your own. You do it on your own, and then we'll go over it. We have some time tonight. You know, it's especially helpful now to have people showing me their faces on their cameras because I can see if you're still working or not. Although Beth could be writing in her journal right now because she's done. Awesome, awesome, awesome. I was joking with my son's kindergarten teacher that with the kindergarten students, they're all like trying so hard to be seen and heard, and they're constantly like, call on me, call on me. And my son's crying. He's like, she's not calling on me. And I'm like, you're not on mute, be quiet. But you guys, like, I don't even know you're there half the time. It's like a whole separate problem. I told her I can't even get them to turn their cameras on half the time. But you guys are pretty good. I don't want to give you a hard time, because some of you are really good about it. Others are shy, and others maybe don't even have webcams. So I feel for you there. All right, let's do this one. We're gonna swap out f of x, change it over to y. And then we're going to interchange x and y. And in order to solve for y, we have to get it out of the square root. To get it out of the square root, we are going to square both sides. So we can undo a square root by squaring, similar to how we can undo a square by square rooting. Have you guys seen this done before? Sometimes I don't know what we remember and what we don't from previous algebra work. Okay. So you can always square both sides of an equation to undo a square root, or cube both sides to undo a cube root. You can do both ways. All right, so we have x squared equals, when you square a square root, you just get that radicand to pop out. And then you end up with y equals, we'll add 7 to both sides, and you have x squared plus 7. X squared plus 7 is just that standard parabola x squared shifted up 7 units. Now, if you remember that, you don't even need to think about anything else because you already know that this is going to be a function. So we'll say f inverse of x equals x squared plus 7. One thing I do want to note to you, and actually maybe I'll wait till the next page to note it because I think it will come up on the next page. Let me verify here. I don't have too much more to do, but yes, it does come up on the next page. So I'll wait, but maybe I'll remember to tie it back into this. Before we move on to the graphing portion, does anyone have a question about any of the stuff on this page? Okay, so the stuff on this page was finding the inverse of a function. Be more specific. Okay, last thing in this section. We are going to use well, we're going to talk about graphing a little bit on this page, but the first thing we're going to do is use the horizontal line test to determine if a function has an inverse function. A function f has an inverse that is a function if there's no horizontal line that intersects the graph of the function f at more than one point. So does the graph represent a function that has an inverse function? So we're going to do that for number 5, and then we're going to sketch a graph that does not have an inverse function. So similar to how we talked about whether or not a graph has a function, we are going to talk about graphs that do not have inverse functions. So does the graph represent a function that has an inverse function? Now, in order to be a function, we have to pass the vertical line test. So does the graph represent a function? That would be vertical line test. That has an inverse function. That would be your horizontal line test. Now, visually, you can think about this vertical line test if you prefer. Definitely, I'm going to just include it here. There's nowhere that you're going to pass a vertical line through here and hit the graph more than once. But you can also tell by the horizontal line test that this graph represents a function that has an inverse function. Because if you were to draw horizontal lines through the graph, you're never going to hit the graph more than one time. So here's where you're hitting the graph. It does not overlap vertically or horizontally. And because of that, we would say that this is a function that has an inverse function. So that means that the inverse of this function is also going to be a function. And in a minute here, when we talk about how the graphs of these two are related, it's all going to come together for you. Does anyone have a question before we draw the graph of the function that does not have an inverse function? Okay. So something like, and here's just one example. I was thinking maybe like a cubic function that kind of has like a twist in the middle, something like that. So this is the graph of a function. It passes the vertical line test. There's nowhere that you'd be able to pass a vertical line through and have it hit the function more than one time. However, it does not pass the horizontal line test. So this would be a function, and we would say it does not have an inverse function. Because of the fact that it would violate this horizontal line test. The horizontal line would go through and it would hit the graph in at most 3 different places. And that's too many. So this graph is a function, but it doesn't have an inverse function. Does anyone have a question about the horizontal line test? Okay. Now, the reason we can use the horizontal line test is because of this property here. The graph of f inverse is a reflection of the graph of f about the line y equals x. What that means is that your function, or your function's inverse function, can be graphed by reflecting your function about the line y equals x. Now, if you're not familiar with the line y equals x, remember it is that 45-degree diagonal that runs through your graph as it moves up from left to right. I'm going to make mine dashed because I want to make sure that it doesn't look like it's actually a line. This is the line y equals x. I want to make sure it appears so that we can use it, but we're going to reflect our function over it. So draw the graph of f. Oh, draw the graph of f. Use the graph of f to draw the graph of its inverse function. Okay, so we'll call this one f of x. And then we are going to draw the line for the graph of f inverse. Now, if I were you, I would not eyeball this. Use some points that actually exist on f of x. Now, because of the fact that our function reflects about the line y equals x, we can actually switch these coordinates out. But I think that you'll be able to see this visually. Like, for instance, we have a spot here on our graph, or a point on the graph at 4, 0, where the graph intersects the x-axis. We have another point at 0, -2. Now, when we reflect this over the line y equals x, what you're going to see here is this behavior where the coordinates are going to switch. Instead of having a point at 4, 0, you're going to get a point at 0, 4. That's going to lie on f inverse. Now, notice that when you're reflecting this about the line y equals x, they're equidistant. And it should, when you eyeball it, it should look right, but use some points to show this. And instead of having a point at 0, -2, put a point on the inverse function at -2, 0. Switch those coordinates. And again, you should be seeing this behavior where that point is reflected over the line. Imagine if you could just take this function and just boop, plop it over the line, and what would you get? That also means, of course, that your graph is going to hit the line at this point. Now, all you need to make a line are 2 points. So connect these with a nice straight line. You have 3 points. Do the best you can. And this will be the graph of f inverse of x. So you're seeing this reflecting behavior not only up here, but also as you move your way down into this third quadrant. You're seeing that all the points should be equidistant to this line y equals x on both graphs. Pretty cool, right? I'll even make a note of that so that we have it on our notes. To draw f inverse of x, switch the coordinates for the ordered pairs. Of f of x. So instead of having 4, 0, we had, and I'm going to label it 0, 4. Instead of having 0, -2, we had -2, 0. So f of x had 4, 0, 0, -2. F inverse of x has 0, 4, -2, 0. So that is something that should be relatively accessible. I know sometimes it's hard to graph these, especially once they start to curve, but we're going to do one with a quadratic function here in number 7. Before I do that, are there questions on number 6? Are you sure? Okay. Okay. I believe you. Right. We are going to graph f as a solid line and f inverse as a dashed line in the same rectangular coordinate space. Use interval notation to give the domain and range of f and f inverse. I thought I had a note here about their domains and ranges. I don't see it now. We'll go over it. We'll talk about it though. Okay. We're going to graph f as a solid line. Now, we have to be really careful with these quadratic functions. Most of the time when they're given to you, it's going to be specified that a quadratic function has a particular domain. Now, I don't want you to find that confusing and be like, wait a second, why is this included? What is this? I can remember being an algebra student and being really confused about what is this? Why is it here? The reason they're chopping this off, you're going to see it graphically, is because they want to make sure that your function has an inverse function. When we graph this, you're going to see that if you don't include this distinction, your function won't have an inverse function. So let's go ahead and graph x squared minus 3, and we're only going to graph it for positive values of x, or x equals 0. Now remember your quadratic function, x squared is your standard parabola. We graphed it a lot in 2.5. We should be really familiar with this. And it's shifted down 3 units. So the vertex is going to be shifted down 3 units to 0, -3. And if you don't remember exactly what the points are on it, if you want to jot one down off to the side, that's fine. I'll do that because why not? Your standard f of x has a point at 1, 1, 2, 4, and 3, 9. Which I'm not going to have space for. But this would be f of x equals x squared. So what we're going to do is we're just going to take that and shift it down 3 units. So instead of having a point at 1, 1, we're going to have that shifted to 1, -2. And instead of having a point at 2, 4, which I should have labeled, we're going to shift it down 3 units, and it'll now be at 2, 1. And instead of having a point at 3, 9, we're going to shift it down 3 units, and it'll be at 3, 6. Now, normally when we draw our quadratic functions, we'll just use symmetry and just have them also, do the same thing on the left-hand side. But we're only graphing these for x is greater than or equal to 0. That's only the right-hand side of our coordinate plane. So go ahead and connect your points with a nice smooth half of a parabola. And this is f of x equals x squared minus 3. Now, remember that had we graphed the left-hand side of this, we would not have passed the horizontal line test. That's the reason why we have this piece here. If you graph the whole parabola, you don't have an inverse function because you can't pass the horizontal line test. I want to make sure that's clear before we graph the inverse. Does anyone have a question about why we have this piece on the function? Why do we specify x greater than or equal to 0? Okay, if we graph for values of x less than 0, we fail the horizontal line test. We want there to be an inverse function. So let's go ahead and switch our coordinates. If you want to label them, if that makes it easier, awesome. We have a point at 0, -3, 1, -2, 2, 1, and 3, 6. I think my labeling might overlap my graph. Let's try to do a good job. All right, so we're going to switch the coordinates. Instead of having a point at 0, -3, we will have one at -3, 0. And you're going to start to see this graph reflect itself over that line, y equals x. Instead of 1, -2, we're going to be at -2, +1. And then instead of 2, 1, we'll be at 1, 2. And instead of 3, 6, we'll be at 6, 3. And that is enough to get you this sideways parabola that actually looks more like a square root function. You know what? I was supposed to use a dashed line. Maybe I'll just show it as being dashed. So this will be f inverse of x. So graph f as a solid line, f inverse as a dashed line. Use interval notation to give the domain and range of f and f inverse. All right, so let's do that. Before we talk about the domain and range, does anyone have a question on the graph? Okay. And if you want to, you may always, give the dashed variation of the line y equals x if you find that really helpful to see your inverse visually. I like to have that there personally. Okay, so now let's list the domain and range. So the domain of f, remember we only graphed f for values of x that are greater than or equal to 0. So we will start here at 0 and go up to infinity. X can be any value from 0 to infinity. Now for the range of f, here's your function f. The smallest y value it can possibly take on is at -3. And the largest y value it can possibly take on goes all the way up to infinity. So we're going to go from -3 to infinity. To find the domain and range of f inverse, switch the domain and range of f. You can also look at the graph to do this. The domain of f is the range of f inverse. The range of f is the domain of f inverse. So you can use that to talk about the domain of f inverse. And you can see that visually. F inverse covers values of x from -3 all the way up to infinity. And that is the range of f. And the range of f inverse, well, here's your f inverse. The range is going to take values of y starting at 0 and then all the way up to infinity. I know it's going to approach very slowly, but it's still going to go that direction. So the y values start at 0 and go up to infinity. So you're seeing here graphically this property that says that the domain of f is the range of f inverse, and the range of f is the domain of f inverse. And that's it for 2.7. Does anyone have a question on number 7 or anything relating to what we discussed today? Okay. My guess is that as I go through and write this test, I'm going to end up in a situation where I'm going to want to email you about something to make sure you have complete directions. I could be wrong. It could be super straightforward. But I probably will shoot you an email this weekend. I definitely will email you just so that you know exactly where your test is going to be at 6 o'clock, because I don't want you sitting there at 6:10 being like, where's the test? I've lost 10 minutes. What's happening? So I will definitely shoot you an email so you know where it is, or where it will be at 6 o'clock. Now, you are going to have to submit your exam to the assignments tab, and I'm going to include that in your email because I want you all to know. Now, for those of you who submitted your graphing homework and you did such a good job and you scanned it on your phone and you got it into a PDF with one file, you already practiced doing this. That's what you're going to be doing for your exam. Even if you do it on your own pages, you're going to be scanning each page, putting it all into one file, and then you're going to upload it to the D2L assignments tab. Don't email me your test. I'm going to put that in the instructions in the email that I'm sending to you. Don't email me your test. I want it on the D2L Dropbox, which is now called assignments. I want you to upload it there. I'm going to have a folder for it. You're going to upload it there, and then I don't want to have to worry about downloading and moving all these tests onto my computer in and out. I'm going to grade it straight from there, and I can put all the comments I need to in there. I don't want to have to worry about all the files. So upload it to D2L. If you did not upload your graphing homework, you might want to practice doing this. I might even just, if you'd like, I can open up a separate folder in assignments just for you to practice dropping things in there. I will do that. I'll just call it Practice Dropbox. And then you can upload stuff in there, and just if you would like to email me and say, hey, just making sure you got this, just so that you can check. I'm going to say this in the email, but I must have your completed test pages within 20 minutes of the time that your exam is over. Your exam is over at 7:50, so that means by 8:10, you have to have had everything scanned in and uploaded and ready for me to grade. If it's not, then too bad. I'm not grading your test. It has to be put in there. Like I said, I don't want to watch you like a hawk, but it's really important for me to know that we're still following guidelines. We're still practicing academic integrity. And the longer it takes, it makes me wonder, what's going on over there? Why is this test taking so long? And if you say, oh, I didn't know how to drop it in the Dropbox, and I was confused about how to do this or that, you may be very well-intentioned, and it's not that I don't believe you, but I can't just be letting students turn in their test the next day, because that gives them a whole night to keep working on it, and that's not fair to everybody else. So I'm going to put explicit instructions in the email for how you're supposed to submit your exam. For at least half of you, that won't be a problem at all because you already submitted homework in the Dropbox. For the rest of you, I'm putting up a practice assignment, and you can practice dropping things into it all day long if you want. Any other questions about Monday? Wonderful. Oh, you guys, I'm letting you go 4 minutes early. Oh, but we have 20 minutes after yes to log in, drop it and all that. Yeah, 20 minutes is excessive, but yeah. Once your test is done, you have a buffer until 8:10 to submit everything. And let me know if you have questions. Don't wait until the last minute to figure out, oh shoot, I have to download that thing to my phone, and I have to figure out how to scan this and make sure it's all in one file and it's in a PDF, and how do I email it to myself? Don't wait till the last minute. Practice it now. Practice it now. Make sure you're ready. Okay. I'm letting you go 3 minutes early. I'll be on until 7:55. If you do have questions, stick around and ask me. Otherwise, have a wonderful weekend. Your homework is going to be on at 7:40 for you to start working on. Adios. Stop my recording.